reaction we've looked at is our deprotonation of our acidic hydrogen. But we started looking at the actual pi bonds reacting. Because of course when we deprotonate our terminal alkyne, we are not actually doing anything with the pi bonds. We looked at our hydrogenation, and we're going to continue looking at some of the reactions of our pi bonds. But again, these reactions are going to be very similar to the reactions that we discussed with our pi bonds with our double bond. So remember, the difference is the fact that we have two pi bonds. So I'm going to start with my clicker question. I know why it does. So the first reaction we're going to talk about today is hydrohalogenations. With our double bond, we're adding an H and an X. And we're going to add that Markovnikov because we're going through a carbocation intermediate. And we're going to get both enantiomers if we do form an enantiomer, so that's just our review. So we can undergo that with a triple bond as well. It's just a matter of how many equivalents we are using. If we use one equivalent, we'll add one H and one X. And again, we're still going to add that Markovnikov, that's what we see. And we're going to discuss the concept of the mechanism a little bit. If we have excess HX, we're going to add two hydrogens and two halogens. Which carbon are the two halogens going to add on? The more substituted. Both halogens are going to add on the more substituted. Both hydrogens are going to add on the least substituted. So that means we're going to end up with a single bond. Notice we can reform a triple bond using this. So we have both halogens adding on the same carbon. Now notice we're only adding hydrogen and our halogen, which is going to be different than when we add our Br2, which of course is going to be only adding halogens. So we still see Markovnikov reaction with this. As far as the mechanism, we might think it's going through just the same mechanism where we're going through this carbocation. And that would explain the Markovnikov reaction. But we learned in chapter 7 that a vanillic carbocation is very, very unstable. Because remember, that orbital was shorter, and this is a positive charge. And our nucleus is positive. So that means that our positive charge is closer to a positive charge, and that's pretty unstable. So it's unlikely that this is the actual complete mechanism that we're undergoing, just because of that. Because a secondary vanillic carbocation would be more stable than a primary, but neither is very stable. And as far as stability-wise, a vanillic carbocation isn't much more stable than a primary carbocation on a sp3 carbon. Because again, that positive charge is too close. But it does explain Markovnikov addition. In reality, the mechanism doesn't really explain all the experimental phenomenon, which in this case is a slow reaction rate, which maybe the fact that the carbocation isn't very stable is going to contribute to the slow reaction rate, but we still wouldn't expect that. But the big thing is, when this was experimentally probed, it was found that the mechanism is third order, and this should be second order. We're reacting one triple bond with one HX, so that should be second order overall. And it was actually found that it's third order, so this doesn't quite explain it. And remember, our vanillic carbocations are very, very unstable. So what's actually likely going on for for the fact that it's second order is that this reaction is actually second order in our HX. Which means that for this reaction to occur, we need two HXs to interact with our triple bond. And this would be termolecular because we have 3 total molecules. So what that would look like, this would be bimolecular, and that doesn't quite agree. So what our termolecular would look like is one molecule of HX has to give up its hydrogen, has to give up its halogen, while another molecule is allowing the triple bond to take its hydrogen. And in that way, we're never forming the full carbocation, so it's a little bit more stable. We still are going to have a partial positive on the more substituted, which is why our halogen attacks the more substituted. In reality, this kind of mechanism is really going to be slow because it's going to take more time for 3 molecules to become to collide in the right orientation to allow this to happen. So that also explains our slower reaction conditions. So we still have a partial positive charge in the more substituted, which still explains the Markovnikov. Now, the thing to note is this is our based on our experimentation that it's third order. But in reality, it's not always so cut and dry. We might have competing mechanisms, and it's likely that we are going to form some of the unstable carbocation on the vinyl position. So some is probably still going through that second order mechanism. And again, we understand what mechanisms are based on experimentation, so that's where that comes from. But the takeaway from it is, if we have only one addition of our HX, we're going to add our X on our more substituted, and we're going to retain that pi bond, because we only use one pi bond if we only have one addition. We also see that we can do the same reaction with our HBr and peroxide with our pi bond for a double bond as we can with our triple bond. Again, if we have one equivalent, then we still retain one pi bond because we're only having the addition of one of the pi bonds of H and X. And it's still going to be that anti-Markovnikov, and we're not going to talk about this mechanism because we haven't talked about the other one. And again, it's a radical mechanism. If we do form the pi bond, we get a mixture of E and Z isomers. That's not really relevant in this one because, of course, this is 2 hydrogens on the same carbon, so we don't have E or Z in this example because we're adding to the most substituted, which means our least substituted already has a hydrogen. If we have an internal triple bond, we're not going to really have any regioselectivity, so typically that reaction isn't very useful. So if we think about this triple bond being internal, we don't have a more or least substituted. So if we're adding HBr, we're going to get the bromine. We're going to have a big mixture of products. With the bromine adding on carbon 3. And in this case, because we would form an E and Z, we'd form both. Plus, we would get the bromine adding on carbon 2. And again, a mixture of E and Z. Because if we have the internal, we don't have any regiochemistry control. We don't have a more or least substituted product. So unless if our triple bond is very symmetric, this isn't a useful reaction, and you would get all 4 of those products. A big mess. Not really helpful in synthesis, because you wouldn't get a very high yield of anything. You'd get a 25% yield of each of those, if it went to completion, which is unlikely as well. So this is not usually synthetically useful, just because we don't have any regiochemistry control. So most of the time, these types of reactions are done on the terminal triple bond because we still have regiochemistry control. Unless, of course, the triple bond is really symmetric and you give the same product no matter which carbon it adds on. But with our anti-Markovnikov, we will typically form an E or a Z isomer, and we're going to get both of them on the least substituted position. And of course, if you use excess, you'll get 2 additions on the least substituted position, and then you don't have to worry about an E and Z isomer. But with our 1 equivalent, we're only going to use up 1 pi bond, so we're retaining the other. Again, still notice we're adding HBr, it's still anti-Markovnikov. It's the same reaction we did before. The only difference is that we are retaining one of the pi bonds because we're starting with 2 pi bonds instead of 1 pi bond. So if we want, and of course if we have excess, then we can use up both pi bonds. We'd still get the anti-Markovnikov addition of bromine. We just get 2 bromines in that anti position. So just a review of that. If we use excess HX, we will get 2 additions of our X on our most substituted. And we can, if we deprotonate it and then react, if we take this, we can reform our triple bond. So that's nice that we can do that. Again, this reaction is only really, really useful if we either have a very symmetric triple bond or a terminal, because otherwise we don't have any regioselectivity. Looking at this example, we're adding H and Cl, and that excess just means excess, meaning we have multiple. So, of our carbons, what's our product going to look like? We're going to be adding what to our 2 carbons of the pi bond? A Cl and an H. How many times are we adding it? Twice, because we have excess. Which carbon or are both chlorines going to be? Carbon 2. So that's what it's going to look like. Notice I'm not showing the hydrogens, but of course I did add the hydrogens. We had 1 hydrogen in our starting material. We have 3 hydrogens in our final compound. If we look at this case, we're forming a triple bond. Now we can only form a terminal triple bond in this case. There's really no question because remember, we don't have any hydrogen in this beta position. And we need 2 hydrogens in our beta position. So here, we're going to form this triple bond. And then the third, remember because we can't mix NH2 and ammonia with H2O because our H2O would just react with our really, really strong base. We wouldn't get a reaction, so we wouldn't form the triple bond. Once our triple bond forms, then we added HBr and peroxide. So in this case, we're not specifying excess, so we're going to assume it's 1 equivalent. And again, what are we adding across the pi bond? 2 atoms. An H and Br. And which carbon is our bromine going to be on? 1, because we have peroxide. Oops. And we are going to get both E and Z because it just depends on which side the bromine comes from, top or bottom. And we can attack on each side. So we will get a mixture. If you look at this example, this is a synthesis. So let's look at the synthesis. The first thing with this synthesis is that we don't have any change in our carbon skeleton. And that's really important now because we do have a way we can form a new carbon-carbon bond if we take a triple bond and deprotonate it and react it with a primary or methyl alpha halide. So we want to make sure we don't have any new carbon-carbon bonds. And we don't. We have the same amount of carbons we started with and we finished. But instead of our 2 chlorines being on carbon 1, they're now on carbon 2. So in that case, we can first form our triple bond between carbons 1 and 2 by doing our elimination reaction. We still have the same amount of carbons. And then we can add our chlorines on carbon 2 by doing a addition. So I numbered them different. And that first step, we can form our triple bond by using our excess NaNH2. with ammonia. Ammonia just helps stabilize everything, and it's our solvent. Followed by water. That's going to form our terminal alkyne. And once we form our terminal alkyne, then we want to do our Markov-Nikov addition, which is all we can do in HCl. We have to specify we're using excess because we're adding two of the pi bonds. So we're using above pi bonds. So looking at this example, we're only adding one equivalent of H and Br from our triple bond, and it's in the Markov-Nikov position. So we know we're starting with the triple bond, and we know we're adding HBr, and we know we're only adding one equivalent. So that would be 8. B, of course, we would be adding one equivalent, but we'd be adding to the least substituted. And then these, we're both adding 2 equivalents, so we would not retain a pi bond when we'd add 2 equivalents of HBr. Remember, our bromines or our halogens are going to add in the same position. It's still going to be Markov-Nikov or anti-Markov-Nikov, whether it adds twice or once. This is another reagent that we've seen before. So this reagent, we're using acid and water. And then notice HgSO4, some mercury. So that should make you think about our hydration. H2O, adding an H and an OH. So first off, this is going to be our hydration. It's going to be slightly different, and we'll talk about what that mercury sulfate is necessary for in a second. So we've talked about hydration. If we had H3O+, we'll add an H and an OH. We will add this Markov-Nikov. And the one thing with this particular reaction is we will get rearrangements if rearrangements are possible. In this example, there's no rearrangements possible, so we don't have a rearrangement. But we're adding an H and an OH across our pi bond. So that's our acid-catalyzed addition, or acid-catalyzed hydration. There's our new hydrogen. So we can do that with a triple bond. It's still going to be Markov-Nikov hydration, but we're going to go through this eno. We're going to have the one addition. Notice to retain the pi bond. However, this will not be our final product because a double bond next to an alcohol is not very stable, and this compound will spontaneously rearrange in the presence of any acid or base, but in this case we have plenty of acid present, so it's going to rearrange to form another compound, and we're going to talk about that in a lot of detail. But this first step, notice we're adding an H and an OH, and of course we started with one hydrogen in our terminal alkyne. We still have that one hydrogen. We added another. Now for this case, it's usually catalyzed by HgSO4 because, again, remember our mechanism of our acid-catalyzed hydration went through that carbocation? Well, a vanillic carbocation is not very stable, so we can catalyze with HgSO4. We're not going to really form a vanillic carbocation because our mercury is going to interact with that partial positive charge. Remember, it can donate electrons. That's going to also prevent any rearrangement, so no rearrangements are going to occur with this reaction. So you do have to have that mercury sulfate as a catalyst, otherwise this reaction is too slow. So we need that. But otherwise, it's still just a acid-catalyzed hydration. So like I said, we will not stop at the enol. And this is called an enol because an ene is a double bond and an alcohol is an ol. So enol. And a carbon that is part of a double bond and has an alcohol attached. So, instead of isolating the enol, which is really not isolatable, this compound is going to rearrange, and it's not a this is not going to be a resonance structure. This is an actual rearrangement. There's a difference. This is going to be two interconvergent structures. This compound is going to rearrange from the enol because it's not isolatable to the ketone. It's going to form a ketone because we attach to the more substituted carbon. So, of course, this is a ketone. A ketone has two R groups attached. So this is what we call our eno-keto tautomerization. And a tautomerization is just a rapid reorganization of our atoms. So let's look at these. Again, I'm going to draw in our hydrogens. So what's the difference between those two compounds? What's the biggest difference? Yeah, where the double bond is. The double bond was between 1 and 2, and now it's between 2 and our oxygen. What's the other big difference? What else does oxygen have attached to the enol? Where is that hydrogen now? On the carbon. So we have a rearrangement of where the hydrogen is and where the pi bond is. And the reason why this occurs is because our carbon-oxygen double bond is more stable than our carbon-carbon double bond. Because our carbon-oxygen double bond has polarity. And we have resonance with our carbon-oxygen double bond. If you recall, and you should, because this class builds up on itself. When we talked about resonance structures, we don't have any resonance structures between a pi bond of a nonpolar molecule because it would be really unstable to have a compound that has a negative charge on a carbon and a positive charge on a carbon in the same compound. Because this is very unstable and this is very unstable. So this is not a contributing resonance structure, and we don't have resonance structures with a carbon-carbon double bond. But with the carbon-oxygen double bond, we have our partial positive and our partial negative. So even though it's not our most contributing resonance structure, our most contributing resonance structure is, of course, our neutral compound, because that all atoms have a complete octet, and we don't have any charge. This is still a contributing resonance structure. And remember, resonance structures give stability. So typically, and you can actually calculate the difference between the stability of this compound and the stability of this compound looking at your bond association energies. And what you'll see is this compound is more stable. So because of that, this is spontaneous. As long as there's a small amount of trace acid or trace base present, this is going to happen. So when you answer these, I do not want this answer, I want this answer. Because this is our final product. But you should be able to draw the mechanism to get from here to here. Now, it's not necessary that the hydrogen that ends up here is necessarily from here. We're going to look at that mechanism. If you were to isotopically label the hydrogens, you'd see sometimes you'd get incorporation of that hydrogen, but oftentimes you'd get an outside hydrogen from the acid. So we're going to look at that as well. Because it's not apparent unless if you specifically label one of the hydrogens where that hydrogen is coming from. Because there's other things in the reaction. But our ketone is going to be what's isolated. We're only ever going to get one addition, and it's going to quickly, as soon as we form the etone, form the ketone, which is why we don't get two additions of this reaction. We only ever get one. Because as soon as the enol forms, it's going to quickly form the ketone. Again, this is another reaction where it's really only synthetically useful if we have a terminal alkyne, because if we have an internal alkyne, we're going to get a ketone on both carbons. We're going to get a mixture of products with the ketone on carbon 1 and products with the ketone on carbon 2. because if it's internal, we don't have any more or less substituting. So this is really only useful for terminal alkynes and alkynes that are highly symmetric. If they're not highly symmetric, then what we're going to get is a mixture of products. So looking at our acid-catalyzed conversion of our eno. So first thing is, remember, in an acid-catalyzed reaction, what kind of charge do we form? There's two kinds of charges. In an acid-catalyzed reaction, what kind of charge can we form? We can only form positive charges in an acid-catalyzed reaction. Because if we formed a negative charge, that would be a strong base, and a strong base would just react with an acid. We cannot mix a strong base and a strong acid. Remember, in an acid-catalyzed reaction, that means that the reaction mixture, the mechanism, is being surrounded by positive charge. So we cannot form negative charge when we are surrounded by a bunch of positive charge. If any would form, it would be quickly reactive. So I never want to see negative charge in an acid-catalyzed reaction. The only exception to that is our conjugate base of our strong acid. Of course, H2SO4 breaks up to form H+, and our SO4H-. The reason why it's a strong acid is because it completely dissociates in water, because that negative charge is so stable. So that's the only negative charge that forms, is our stable conjugate base. Otherwise, on our organic compound, we're never going to form negative charge, because as soon as negative charge would form, it would just react with the acid. So in that environment, a negative charge is too unstable to form. This environment stabilizes positive charge only. Just like in a base-catalyzed reaction, we only form what kind of charge? Negative. Because as soon as a positive charge would form, the base would react. So it's very important. That's called mixed media. A mixed media, when we're writing our mechanism, is we're not going to mix positive and negative charge. We're not going to mix a strong base and a strong acid together. What happens when you do that in the lab? If you just poured a strong base and a strong acid together quickly? Explosion. So think about that, but that's what's happening. You won't cause an explosion because when you're drawing your mechanism, you're mapping out what's most likely to occur. Very unlikely you're going to form a strong base in acidic media. It's too unstable, that energy would be too high. So our mechanism will only have positive charge if we're doing an acid-catalyzed mechanism. So here we have our eno, and we have acid. And this is being shown by H3O+. Typically we're using H2SO4 because our conjugate base of our H2SO4 that's a negative. It's very stable and it's non-nucleophilic. So HCl could be used, but remember Cl is nucleophilic. Sorry, H2SO4 is next. H3PO4 as well. But that is being stabilized by the fact that it's very stable and we don't even need to draw it into mechanism. We have our H2O+. But of course that's floating around as well. So we have our H3O+, we have an acid. What's going to be the most likely thing that's going to happen? So the question is, we have a partial positive hydrogen on our acid, and something's going to deprotonate it. That's going to be our first step. We have an acid present. So the question is, what's going to deprotonate it? In this case, the alcohol could deprotonate it, but that won't lead to our final product. And it would be reversible anyhow. But our pi bond is also a weak base, so we can deprotonate it. So we have two places that can deprotonate our acid, either our oxygen with our lone pairs on our OH, or our double bond. If our OH deprotonates it, that could form, and it might form in the reaction, but there's nothing else that can happen with this. We can't get an SN2 reaction because we have a double bond, and that doesn't occur in a double bond. So that's stopped. That mechanism won't go anywhere. This is probably forming, but it's highly reversible, and water that forms is just going to move that hydrogen to reform our starting material. So I'm not saying that that doesn't happen, because it's likely happening in the reaction. But it's highly reversible. Nothing else is going to happen. There's nothing that can push off that water as a leaving group, because we won't get an SN2 reaction on a vinylic carbon. So what's more likely is the reverse will occur pretty quickly. So this might happen, but it'll go backwards. So that's not going to lead to our final mechanism. Just because it's not leading to our final mechanism doesn't mean it's not happening and going back and happening and going back. It likely is. But we're not really concerning ourselves with it. So that's a possibility, but that won't lead to our product. The other possibility is, of course, we have a pi bond that can deprotonate. So that'll form our positive charge here, and that means that we protonated that carbon. So that's what I said, that hydrogen might not be coming from the OH. It's likely coming from our acid, from outside. So now we have a positive charge next to an oxygen that has lone pairs. So what's likely to happen is we're going to get the formation of our carbon-oxygen double bond, because this is resonance. This resonance stabilized, and of course our more contributing resonance structure is this one, because all atoms have a complete octet, versus this one, our carbon doesn't have a complete octet. So now we have that oxygen with a positive charge, and remember we have water floating around because water is our solvent, so that can come in and deprotonate, and that forms our ketone. And this reaction is equilibrium based on the fact that our ketone is more stable than our phenol. So this happens pretty rapidly under these conditions, and we isolate our ketone. So you should be able to draw this mechanism. This can also, and this is called a tautomerization, and it favors the ketone greatly, and it's very difficult to isolate the phenol unless if something else is stabilizing that double bond, like being in resonance with other double bonds. So in almost all cases, we're going to isolate the ketone, and that's what I want to see as your product if I give you the single-step synthesis. It's always going to be the ketone. The alcohol is still adding on the Markovnikov position, the more substituted. And it is different than resonance because these are two isomers of a compound. They're not the same compound. They are isomers. They have different connectivity. This can also be done under base catalyzed conditions, and I'll show that in a second. But as I was saying before, an internal triple bond isn't as useful for this reaction. Neither are more or less substituted, so we're going to get a mixture of the ketone being on carbons 1 and 2. And unless this is highly symmetric, so these two compounds are the same, this really isn't useful synthetically. So this is most useful on our terminal alkynes. So looking at this example, we're going to get both products because we don't have any control. But with this first example here, the second example, we have, and this is just showing it, we're going to have a ketone forming on carbon 5 and carbon 6. With the second example, of course, it's going to be Markovnikov, carbon 2 is more substituted. So we're still going to isolate our ketone. Now, in this case, I'm just going to show you this. Notice BH3THF, H2O peroxide of sodium hydroxide. What's that? Our anti-Markovnikov addition. So here, if we have a terminal alkyne, we're going to get the alcohol form the anti-Markovnikov. Notice we still have an enol. So what do you think is going to happen? It's going to form, technically, and this is terminal, it doesn't form a ketone, it forms an aldehyde. Because the terminal alkyne has a hydrogen, which means our alcohol adds to the carbon that has a hydrogen. Which means this has a hydrogen, and this is called an aldehyde. As soon as there's one hydrogen attached to a carbonyl carbon, acetyl-1-O, that's an aldehyde. So technically it's an enol-aldehyde tautomerization, but the same concept. And the big difference here is that this is under base conditions, sodium hydroxide. So the mechanism to go from here to here is slightly different. Because under base catalyzed, what's not going to form? Positive charge. This is going to undergo a negatively charged mechanism. And I want you to think about that mechanism for that one. So that's where I'm going to leave you with. Think about that mechanism. And we're going to go through it on Wednesday. And you should be able to draw both of those. Oh, if anyone's interested, we're having a chemistry club meeting on Wednesday at 5. And our department barbecue is Thursday at 4:30. I'll be posting a thing about the chem club meeting online.